In this review, we'll be going over continuity. Continuity, the definition is that a function for any value of x must give a value of f of x. First example we're going to look at is f of x is equal to the square root of x minus 8. Now the first thing that should jump out at you when looking at this problem is that we have a square root. Square roots can only have a positive value inside of the root. So if we were to put a value in here that would make this inside negative, then we would not get an f of x. Therefore, this function is not continuous. Although we can restrict it to say that if the inside here is greater than 0, or greater than or equal to 0, so x minus 8 is greater than or equal to 0, or solving for x, x is greater than or equal to 8, we can say that f of x is continuous on the interval of 8 to positive infinity. If you're unfamiliar with this notation, the bracket here, the square bracket, means that we include 8 because it's greater than or equal to 8. And the parenthesis here means we approach infinity but never get to infinity because, of course, we can never get to infinity. Next example is going to be f of x is equal to the third root of x minus 8. Now this example, the root might pop out at you as something special again, but because it's an odd root, remember that odd roots are continuous everywhere. So because the odd root is continuous everywhere, that's the only thing that would affect continuity. This is continuous. The next example we'll be looking at is f of x is equal to the absolute value of 4 minus 8 over x to the fourth plus x. Now if we review this chapter, we'll find out that the absolute value function is a continuous function. So out of the two things that would pop out of you as somewhat different in this problem would be the absolute values and the fraction. But because the absolute value function is continuous everywhere, the only thing that would affect it is the bottom of the fraction. So the bottom of the fraction cannot equal 0, otherwise we'd have an undefined ratio. So this function is not continuous. Now once again we can state an interval for which this function is continuous, and that will be from when x to the fourth plus x is not equal to 0. This function will be continuous. Solving for x, let's factor out an x. So x cannot equal 0, and x to the third plus 1 cannot equal 0, or x to the third cannot equal minus 1, taking the third root of each side. X cannot equal minus 1. So we have two instances where x is not continuous, so we can state that f of x is continuous on the interval of minus infinity up to negative 1, but not including negative 1, union, or also including negative 1, but not including 0, and then from 0, but not including 0, to positive infinity. The next example we'll be doing will be kind of a review. We'll have to use everything that we've learned so far. What we're asked is if we have a function f of x is equal to 9 minus x squared when x is greater than or equal to minus 4, and kx when x is less than minus 4. What value of k will make this function continuous everywhere? Now, because we have a polynomial up here, we know polynomials are continuous everywhere. We also have a polynomial down here, which we know are continuous everywhere. So the only place where f of x might not be continuous is at x equals 4. So in order to make this continuous, f of x of 4 must be equal from the left as it would be f of 4 from the right. So what we're going to do is we're going to set 9 minus x squared equal to kx at x equals minus 4. So let's just put in minus 4 for x, and then just plug and chug. So we have 9 minus 16 is equal to minus 4k. Solving for k, we get k is equal to 7/4. So f of x is equal to 9 minus x squared when x is greater than or equal to minus 4, and 7/4 x when x is less than minus 4. This function is continuous everywhere. Thank you.